I come home in the morning light. My mother says, when you gonna live your life right? Oh mama dear, we're not the fortunate ones.
We have seen how a current running in a conductor produces an electric field in the manner shown in this figure. But we have not expressed the magnitude of this field. Apparently it changes as a function of radius. And without going into the derivation of the field strength, we'll just state the result. So the magnetic field strength at some distance r from the conductor, which is considered to be long or infinite, is mu naught divided by 2 pi times the current. We'll call this, okay, just I, divided by the distance r. Mu naught is a physical constant called permeability of the space, and it has the value of 4 pi times 10 to the minus 7 Tesla meters per ampere. As you can see, the field strength decays as a function of r. For a simple case of one conductor, the calculation of the magnetic field is quite straightforward. Here we have the magnitude, and as you know, magnetic field is of course a vector quantity, so it has a direction. And the direction is always tangent to these field circles, if you will. So for example, at this point, the electric or the magnetic field would be pointing that way in the plane of these circles, and here in this direction, and so on. So for example, if we want to sum the field in the case that we have two conductors, we have to calculate the vector sum at any given point. So for example, if we have two connectors where the fields are, or the current is running into the page, so here's I1 and here would be I2, according to the right hand rule, the field of this one would be going like this, clockwise, and the same thing with this one. Also clockwise. So then if we take a random point, for example here, first we have to evaluate what is the field due to I1. So it's at this distance, it's tangent to this circle, so the V1 would be something like this. And the field from I2 would be going in this direction, something like this. So in general case, we always have to consider the vector sum of the two fields. And in certain points, these vector sums become pretty easy, as we shall see. Let's calculate a simple example where we want to evaluate the magnetic field strength created by a lightning bolt. So B is mu0 divided by 2 pi times the current in the lightning bolt, and then some distance away from the lightning bolt. So we have 100 amperes estimated current and the magnetic field is evaluated 10 meters away. So mu0 4 pi times 10 to the minus 7 Tesla meters per ampere divided by 2 pi times distance 10 meters, and then we have the current 100 amps. So amps cancel, meters cancel, and we are left with Teslas, which is what we want. So here we have 2 times, so these that will cancel, that only leaves 2. 2 times 10 to the minus 7 times 100, 2 times 10 to the minus 5 divided by 10, that's 10 to the minus 6 Teslas, which is 2 microteslas. And the question is, would it have a significant effect on compass? The magnetic field of Earth, let's say at the equator, is about 50 microteslas. So no, the lightning wouldn't significantly disturb a compass. If you're that close to a lightning bolt, there are bigger issues to worry about. In this figure we have 2 conductors and their respective magnetic fields. As you can see, on the left the current is coming out of the screen, and here on the right the current is going into the screen. So according to the right hand rule, at this middle point, both of the fields are pointing in the same direction. And here the magnetic field strength would be just the sum of the 2 magnitudes. So the vectors b1 and b2, because they point in the same direction, their vector sum is just the magnitude of the 2, and the direction, of course, upwards in this case. But here in this exercise we are asked, what if I1 and I2 would both point into the page? So also the I1 would go into the page in this manner. So according to the right hand rule, the B1 would be a circle rotating in counter or clockwise direction. So at the midpoint, the B1 would be pointing downwards. Also, on the right hand side, the current is going into a screen, so it's also a clockwise field, but at the midpoint, the B2 is pointing upwards. As always, in a general case, we have to calculate the vector sum, but because they are parallel, the vector sum is just or the magnitude of the resulting vector is just B2 minus B1 if we choose our positive direction to be that way. And as we can see from this example, the B2 is greater in magnitude, so the resulting vector would be also upwards. So we would have total field B something like this.